This is section 12.8 on similar solids, and we have two different prisms, and not all prisms are similar to each other, so we have to do a few checks to see if in fact they are similar because we have a specific definition for what we're looking at here. First of all, they're both prisms, they're both rectangular prisms, so that's good. You couldn't have a pentagonal prism similar to a hexagonal prism. And then we have to see if all of the ratios are the same. In other words, 40 is to 80, just as 4 is to 8, and just as 12 is to 24. And we call this a linear ratio. The ratio of all of the linear measurements or segments are in a ratio of 1 to 2. So that means that yes, these two prisms are going to be similar to each other. If I ask the question, how many times bigger is the second prism than the first one, you might say it's twice as big because the linear ratio is going from this direction 2 to 1. Or since maybe these represent swimming pools with the blue surface on the top, you could say that this one is twice as big as that one because the surface area is twice as big. In other words, 24 times 80 is 4 times bigger than 12 times 40. So we could say the linear ratio is 4 to 1. But probably the best answer to that question that I phrased not very precisely is how much bigger is this prism than that one would be in an 8 to 1 ratio because the volume of this one is 8 times bigger than the volume for that one. If you think about it, we're going to multiply 80 times 8 to get the area of the base times the height, which is 24. So this is twice as big as the 40. This is twice as big as the 4. This is twice as big as the 12. So each one of these measurements is 2 times bigger. So twice as big times twice as big times twice as big, it's going to make it 8 times bigger. And in general, when we have similar solids, we look at for three different ratios. The linear ratio we call A to B. In this case, we called it 1 to 2. So then if you square those numbers, square the 1, square the 2, the area ratio is 1 to 4. This area is 1/4, as big as the big one. And then we could cube those original numbers. So 1 cubed is 1, 2 cubed is 8. So the ratio of the volumes is 1 to 8. Spheres are always going to be similar to each other. So I have two spheres here. One has a radius of 9, one has a radius of 6. The question is, what is the ratio of their volumes? So we don't ever actually have to figure out the volumes, though we could. The volume of this one would be the 4/3 times pi times 9 cubed. The volume of this one is 4/3 times pi times 6 cubed. And if you start simplifying those things down, the 4/3 pi cancel out. We get 9 cubed over 6 cubed, which is going to simplify down then to this 27/8 answer. Next question asks, are these cylinders similar? So not all prisms are cylinder. We have to do a thorough check. Yet all spheres are similar to each other because they all do have the same shape. So are all cylinders going to be similar to each other? They have kind of the same shape in that they have circular bases and they have perpendicular heights to them. But do they meet the more specific definition? In other words, are all the ratios the same? So if I look at cylinders A and B, we have a 2 to 1 ratio of the height, but the diameter ratios are 1 to 1. So A and B are not going to be similar. We look at B and C, we have a 2 to 1 ratio of their diameters, but the heights are in a ratio of 1 to 1, so they're not similar. We could also check cylinder A with cylinder C. We have a 2 to 1 ratio of the height. We have a 2 to 1 ratio of their diameter. So I would say yes, A and C are similar to each other. Right, in this next example, we have two what look to be like rectangular prisms. If nothing else, this little symbol between us tells them that they are similar to each other. And we're given the volume for the one on the left, the volume for the one on the right, and the question is, what is the scale factor? In other words, we have this volume ratio that we can figure out. From there, we want to know what is the linear ratio. In other words, how does this segment compare to that segment? So to begin with, we are going to set up our volume ratio. The A cubed to B cubed, the ratio of the volumes, I just wrote those numbers down. And we want to get to the linear ratio, so we're going to take the cube root of both of those, the cube root of the numerator divided by the cube root of the denominator. And then we can simplify this however we like. Eventually, we're going to get down to a ratio of 2.52 to 1. So all of the sides in this segment corresponding to the same side in the other one are approximately 2.52 times bigger. All right, I'd recommend that you pause the video at this point and see if you can work through this one. We have this cone. We want to find the volume of a similar cone, which changes by a scale factor of 2 to 3. In other words, 2 units of this one are equal to 3 in the other one. And I'm going to explain it using those ratios of the volumes. However, you could figure out what the diameter of the other one would be and the slant height of the other one would be. In other words, multiply by 3 halves, multiply by 3 halves, and do it. I'm going to find the volume and then use the ratio. So again, I pause your video, see what you can do. What I'm going to do is first of all find the volume of this cone. There's my formula. If I plug in the numbers, 18 is the diameter, so 9 is the radius. This is the volume of this cone. The A to B ratio we were told was 2 to 3. So that means that the A cubed to B cubed ratio, cube the numerator, cube the denominator, is equal to the actual volume of this one, the 1080 pi divided by x, where x would be the volume of the cone that we want. So now if you cross multiply and solve for x, there is the volume of that other cone. All right, next example, we're told that we have two prisms that are similar to each other. We're told the volume and the surface area for prism A. I don't know what kind of prism it is, but that doesn't matter. I'm told the volume of prism B, but I don't know its surface area. So we have to use those ratios this time, and that's why I wanted to use the ratios on the last one to get an idea of how to use them. To begin with, the volume is in the ratio of A cubed, B cubed. So I'll go ahead and write down my two different volumes. 1000 over 800, and that simplifies to 5/4. So then we're going to take the cube root of those two numbers to get to the linear ratio, the cube root of 5 over the cube root of 4. We went from the volume to the linear, and the linear is the key one because it connects to get us to the surface area ratio. So A to B becomes A squared to B squared because we're talking about an area ratio. So square the 5, square the 4. So the ratio of the surface areas is the cube root of 25 over the cube root of 16. And the actual surface areas we have are 750 over x, the unknown. So the next step is to cross multiply, and we get x is approximately 646.33, and that label would be in units squared. And then in this last example, I would work through the problem. You can see my final answer right here. There's different parts. Find the volume, and I'm asking for the volume here, the volume of the top frustum, the volume of the cylinder below it, add them together, and we have our total volume for the shape that kind of looks like a funnel. Again, all the work is here, just to break it down into pieces.